All right, hello everyone. So today we're finishing chapter 23, and we're specifically going to be looking at full circuit analysis. Well, what does that mean? Well, we reviewed last time that means finding really the amount of current that's going through every circuit element and finding the voltage drop across every circuit element. We'll also explore how a digital multimeter works, or a DMM, and also we'll look at some applications with RC circuits, which means resistance and capacitance. Very good. For our next lecture, we'll be taking a look at magnetic fields and starting chapter 24. Homework number 8 on chapter 23 is due Wednesday, March 25th, and the homework number 9 will be due right after spring break on April 8th. Let's take a look at a more complex circuit than we did before. Before we just looked at a resistor that was in resistors that were in series or resistors that were in parallel. Just to remind you from last time, we had some resistors that were in series with each other, and here was some resistors that were in parallel, and we reduced them to kind of just a single resistor element. So if you need a review from that, please see the lecture from last time. What if we were to have a more complicated circuit like this? What do we do? Well, the strategy is basically this. You're trying to reduce these circuit elements here down to one resistor, combine them here with this one, and then notice that this whole set of 3 resistors is actually in parallel with this one over here. So putting it all together, I'm going to first look at this drawing here, this circuit here, where I have the different resistors, and the part that I've circled right here, I'm going to reduce that to something that is 18 ohms. Now, how did I get that? Well, I basically said, okay, 30 ohms with a 45 ohms in parallel, they're going to add like 1 over. So if you remember, our strategy for adding resistors in parallel with each other is to add 1 over the first resistance plus 1 over the second resistance is equal to 1 over RT. Don't just stop there at adding up 1 over. You need to finally take 1 over that result to get the 18 ohms. I encourage you all to practice that on your own and make sure that you're feeling confident with that. Finally, I ended up with 18 and 42, which together make a 60 ohm resistor. And then I add that with a 40 ohm resistor in parallel. So again, once more, I need to do the calculation 1 over 60 plus 1 over 40. Just computing that out here, we'll do 1 over 60 plus 1 over 40, and then I'm going to take that number to the minus 1. So we get 24. So 24 ohms is our equivalent resistance to this whole mess over here. So this big mess ended up reducing into a resistor that has a resistance of 24 ohms. How about that? Okay, what if things got even more complicated? What if you had more than one voltage source? What if you had a bunch of different resistors around? How do you handle a situation like this? Well, same as we always do. We're going to basically reduce each part piece by piece. So for example, taking this part, reducing it down to 1 resistor, combining it with this one, then combining over here, and then finally we realize that all 4 of those elements are actually in series with each other. So the 12 volt, the 3 ohms, the 3 volt, and then this big old thing here are all in series with each other, so they can be slid around. So in pictures, we've taken this result here, look at these 2 right here, the 4 and the 12, and we reduce them by adding them in parallel with each other to a 3 ohm. Combine these 2 together and it becomes an 8 ohm. Combine the 8 ohm with the 24 ohm and it becomes a 6 ohm. And then finally, the 3 and the 6, they can slide around. It doesn't matter that there's a battery between the 2 of them. Those 2 add in series and they become a 9 ohm resistor. So you get now an equivalent resistance in your circuit. That allows you to figure out the amount of current that's going through the circuit. And then ultimately, you can start putting back the resistors together, and you can put them piece by piece back together to get a full circuit analysis. Let's take an example that would be something more realistic from a laboratory. Maybe some of you are doing research in biology or kinesiology where you need to keep something at a certain temperature. And so one strategy for doing that is to have a wire, for example, the nichrome wire that we had talked about in previous examples. And you're going to connect that to a battery and then allow that to provide some heat. So the question right now is, what power does the resistor in this case provide to warm a solution? So let's say you needed to grow some bacteria in a petri dish and it had to be at some temperature, or maybe that you were trying to keep something warm so that that a chemical process would take place. So in this case, we should take a look at our circuit here, and we should also just remind ourselves of two important formulas. One is that V is equal to IR. The other one is that power is equal to voltage times current. Now I could plug in for this IR for V and remember that we could get I squared times R, or I could rearrange this formula as I is equal to V divided by R, and I could also plug in this I in for here, and I could also say that this is equal to V squared divided by R. So V times V over R, which for I gives me V squared over R. So those are some, possible ways of rewriting things. And in the case where I have a 9-volt battery connected to an 18 ohm resistor, I can see pretty clearly here that I've got a voltage and I've got a resistance, so I can calculate the power as V squared over R is going to be equal to 9 volts squared divided by 18. Well, let's use a calculator to figure out what that is. 9 squared divided by 18 is 4.5. So that means 4.5 watts. And remember that a watt is equal to a joule per second. That's what the meaning of a watt actually is. And you saw joules before when you took the mechanics introductory physics. Is 4.5 watts a lot? Well, put it in perspective. If you wanted to heat up your water, let's say you have maybe one of those little electric water kettles that heats up your water so you can make tea or coffee, and you turn it on and it boils your water. So if you heat up your water in about 5 minutes, that kettle is using about 1 kilowatt. And so this is about 5 watts, so that's about 200 times less. So it's not nothing, but still it's quite a bit less than an electric water heater. Okay, so the second part of this question was asking, well, what if I wanted to, let me kind of move this down here. What if I wanted to heat up this solution more quickly? So the investigator decides that the warming is happening too slowly, and she has another resistor, but she doesn't have another battery. So what can we do to connect both the resistors into the battery into a single circuit that increases the amount of power that's dissipated? Well, if we know our power is V squared over R, V squared over R, we know that I can either increase the voltage, right, or I can decrease the resistance. So you can say, well, what could possibly decrease the resistance if I'm going to add another resistor in there? And then you might remember, oh yeah, if I added a second resistor in there, 18 ohms, I will decrease this resistance and overall increase the power. And that's what I want. So putting them all together here, we can see that 1 over resistance total is going to be equal to 1 over 18 plus 1 over 18. If I add those two together here, I'll do 1 over 18 plus 1 over 18, and then I'm going to take 1 over that number, 0.11. So I get 9 as my result here. So in other words, our total is equal to 9 ohms. So in other words, by adding the two pathways, we actually have half the resistance. So that's interesting. That means if half the resistance, that means that our power is going to be equal to 9 watts. one way to look at that would be, you could say, well, now I have an equivalent circuit which has a 9-volt battery with a 9 ohm resistor, in which case you could say, well, I is going to be equal to V divided by R, so 9 divided by 9 volts divided by 9 ohms, which is 1 amp. And you could say, well, through this we have now 1 amp going through this thing, 1 amp going through this, and 9 volts is our voltage. So you could say power is equal to voltage times current, which is equal to 9 times 1, so that's 9 watts. So that's another way to look at it. Or you could plug into V squared divided by R, where R is your R total. And if you plugged in 9 squared divided by your 9 ohms now, you'll also get 9 watts. So just wanted to point out that these are the same, and that you will get the same answer no matter which way you approach. Very good. So we've helped our investigator to heat up their solution. Let's talk about some of the ways that we can measure current and voltage. And so to do this, I'm going to actually go back to the PHYS simulation here. So if you, for example, type in on Google PHET simulation circuits, or I think even if you just typed in PHYS circuits, yep, sure enough, then the first thing that comes up is this circuit construction kit. It'll open in almost every browser. You don't need to install anything. And I'm going to go here to this one called Lab. And the reason why I did that is because in the intro one, it just gives you this kind of current meter, whereas in the lab one, it gives you the real current meter that's more similar to what we actually use in our teaching laboratories. Okay, so here's our sort of setup here. I've got a battery, I've got a wire, now I've got another wire. I'm just using a little extra wire here just to kind of, make the point. So if I connect this guy here we've got ourselves a light bulb. I can bring it down here too if I wanted to. And if I wanted to bring a voltmeter here, I can actually connect it to this side and this side, and I'll see that it's 9 volts, and it's a 9-volt battery also, and it's a 10 ohm resistance. So you can probably do this one in your head. What's the current? Well, current is voltage divided by resistance. And if the resistance is 10 ohms, it's 9 divided by 10. So 9/10 of an amp is what we'd expect. Now, if we want to measure current, we actually have to break the circuit. We can't just simply put this thing on here and expect it to measure the current. We actually have to send the current through our ammeter in order to detect the current. So something like this will do the job. And sure enough, it measures 0.9 amps. So the ammeter must be placed in series with the current that's being measured, and the resistance of the ammeter should be 0, or at least really close to 0. Oops. There we go. So you can see that here I have the current is flowing through the ammeter. And if the resistance of this ammeter was not 0, then it would actually change fundamentally what's happening with the circuit. We don't want that to happen. Now look at the way I've placed the voltmeter here. A voltmeter is going to be used to be measuring the potential difference across a circuit element. And it's actually placed in parallel with the circuit element. What about the resistance of an ideal voltmeter? What do you think that resistance should be? Well, if it had some small resistance, then instead of the electrons flowing through the light bulb, they would flow through the voltmeter, and it would change the circuit. So therefore, we can see that the voltmeter itself has to have a very high resistance. This means that it won't affect the circuit that it's interacting with. It'll just measure it, kind of like, without interrupting or without changing what's going on inside the circuit. So that's how we measure voltage and current. So what if I gave you a circuit like this and told you, well, I'm going to hook up this voltmeter here. Is this the right way to do it? What would the current in the circuit be? what does the voltmeter actually read? And if this is not right, how would you change the voltmeter configuration so that you can measure the potential difference across the resistor? I'll give you a moment here to pause. Okay, so we're back. The way that I would look at this here is to say, well, I've got this voltmeter, and I think that this voltmeter, since it's got an infinite amount of resistance, or, well, it's really, really large resistance at least, it's going to stop the flow of current through this circuit. So current might go up through this thing, and this says, oh, wow, this is a very, very large resistance. I'm not going to make it through. So there won't be any current really, no appreciable current at least, that makes it through this circuit. Well, will there still be a voltage measured? There will be, but it'll treat this resistor as if it was a wire. So it'll actually measure the 9 volts here and then 0 volts. So it'll measure a voltage difference of 9 volts. But it's not really measuring the voltage across the resistor. It's just measuring the voltage of the battery in that case. So I would say there'd be very, very little current, almost 0. And the voltmeter reads 9 volts, but it's not really measuring the voltage across the resistor. How would we change this circuit so that we're actually measuring the voltage difference across the resistor? I would pick something like this, where the voltmeter really is measuring in parallel across the resistor. Let's take a look at another situation. What if we had an ammeter that we hooked up like this? In this case, is there current that's flowing through the 5 ohm resistor? Well, in this case, since the ammeter has a very, very little resistance, or we could say almost 0 resistance, then we'll be set basically by the current that's flowing through the 10 ohm resistor, and then when it gets to this junction, it's going to choose to go through this ammeter and not through this resistor here. So in my little simple drawing, it should look something like this: a 9 volt battery connected to the 10 ohm resistor, and then almost ignoring this guy as if it didn't even exist, goes straight through the ammeter and back. And this is something that's very close to 0 resistance. Okay. So our current is going to be 0.9 amps in this case. It's the same as the PHYS simulation. And interestingly, we have to make some change in our circuit in order to actually measure the current that is going through the 5 ohm resistor. If so, imagining that this ammeter was not there, we need to place the ammeter in series with both the 5 ohm and the 10 ohm resistor. What would this actually look like? I propose something like this. In this case, the 9 volt battery is connected to the 10 ohm resistor, 5 ohm resistor, and then in series with the ammeter. In this case, I is equal to V divided by R total, where R total is 10 plus 5 ohms. So 9 over 15 is going to be 0.6 amps. So 0.6 amps in this case will be the new current that's going through the 5 ohm resistor and through the 10 ohm resistor. Okay, so now we're moving along to looking at combinations of capacitors or groups of capacitors. Well, we've looked at groups of resistors, and we saw what the rules were for resistors. When they added in series, they just added directly, and when they added in parallel, they added like 1 over. One thing that you might notice here is that it works exactly the opposite for this situation for capacitors. In other words, capacitors that are in parallel with each other, if you remember, there's a formula that basically says that the capacitance of the capacitance was equal to epsilon naught A over D, right? And this A was the area, right? So if you had a couple of capacitor plates that were connected to each other, right, like this, right? It's like almost as if they're connected across like this, right? And so then the area effectively is getting larger. So the way I like to think about it is that that's why, or at least that motivates why, adding up the capacitors in parallel, they just add directly. So if you had, 3 times as many capacitors in parallel, then you have 3 times the capacitance. Capacitors in series, they add just like resistors added in parallel. So it's a little backwards, and you're going to add up 1 over one capacitance plus 1 over the other plus 1 over the other, however many there are, and then you're finally going to take 1 over that. So let's practice. Which of the following combinations of capacitors is the highest capacitance? So take a moment, please, to pause and to work it out. Just imagine that each capacitor here has the same amount of capacitance. You could say 1 farad, for example. Okay, I just realized that I showed you the answer. Well, hopefully that didn't deter you from actually trying the problem. Let's take a look here. If I just had 1 capacitor here, I'm going to say that's going to be 1 farad. If I have 2 capacitors that are in parallel with each other, those are just going to add directly. So adding 1 plus the other one, so 1 farad plus 1 farad is 2 farads. If I have the 2 capacitors that are in series with each other, I'm going to add like 1 over. So 1 over 1 plus 1 over 1, and then finally take 1 over that, so the inverse. And so that becomes half of a farad. Now things get a little trickier here. I've got I have this thing that's in series with 2 that are in parallel. So first I've got to do that same kind of reduction thing where I'm taking the 2 in parallel and adding them together. So that just adds directly, like up here, to give me 2 farads. And then that 2 farads and the 1 farad, they need to add like 1 over. So that's going to give me 1 over 1 for this one, plus 1 over 2 for this one, and then take 1 over and take in the inverse of that. So that's going to be 2/3 farad. Okay, very good. So, so which the one is the largest one? It's B. B is the largest. The next largest is just a single capacitor. Then it's this one here, the last one, I guess, which is what, E? No, is it E? Sorry, just a second. D, and then C. So B is the biggest capacitance. Okay, let's take a look at a little bit more challenging problem now. What would happen if I connected these capacitors? What kind of situation would I end up in? What would be the effective capacitance across all of these here? Please pause and see if you can figure out the equivalent capacitance between this point over here and this point over here. So in order to solve this problem, we should combine these two as parallel resistors, which means they just add, and then finally we should combine that in series with this 10 microfarad capacitor. So the way I'm going to handle this here is I'm going to say that I have 20 microfarads with 60 microfarads that just add together to make an 80 microfarad capacitor. Then I need to do some work to actually combine this 80 microfarad in series with the 10 microfarad capacitor. So how do I do that? Well, I'm going to do 1 over 80 plus 1 over 10, and then when I finished putting those together, then I'm going to take the 1 over that combination in order to finally get my my answer. So putting those together, I'm going to take 1 over 80 plus 1 over 10, and then I will do 1 over that answer. So let's try that here. So I'm going to do 1 over 80 plus 1 over 10, and then I'll take that to the minus 1. Or conversely, another thing you could do is take 1 over that. So I'm basically getting about 8.9, and 8.9 will be the equivalent resistance between those two terminals. So this here and this here. So 8.9 microfarads. And you notice that one of the things that was nice is that if I just stayed in microfarads the whole time, that I know that my final result will be in microfarads. Very good. Now let's talk about RC circuits. So in an RC circuit, we're going to have a situation where we are going to either be charging or discharging the capacitor. So imagine we have this situation where we have a capacitor that's all charged up. Imagine I maybe hooked it up to a battery a few moments ago. And then we're going to connect it to a resistor. Well, what happens? In the moment that we connect it, we're going to see a large amount of current that flows until finally all those positive charges meet the negative charges and balance the charges in this capacitor. So you could imagine that there's going to be a lot of current, and then less and less and less until the charges balance themselves out. So this is what the current looks like: is that there's no current initially, and then the moment you close that switch, then there's a maximum amount of current, which is actually given by V divided by R, and then that amount of current decays. The amount of voltage is the amount of voltage across the capacitor, and that steadily decreases like this. And it does so by a decaying exponential, which is e to the minus t over RC. And I just wanted to show you something that might be helpful for problem solving at some point. Go ahead and get a blank page here. Writing out this I is equal to I naught times e to the minus t over RC. I just wanted to just show you a thing that maybe is helpful. Some problems might ask you the other way around. They might say, well, what's the time that it takes to do something? If I just rearrange this as I over I naught is equal to e to the minus t over RC, you might be familiar with the natural log function. Natural log is also written as ln. So this is, I'll write it as this is the natural log. This means log base e. And if you take the log of both sides here, log and e, they undo each other. So that means that the log of e is just 1. And if we have the log of e to the 3, then that 3 actually can just come down since it undoes each other as functions, and that'll just become 3. So in other words, this becomes minus t over RC is equal to I over I naught. So in other words, now you have t written as some other things. So we can, we can like kind of rearrange some things here, but I think you get the idea is that you can rearrange and you can figure out the amount of time that it takes to reach a certain intensity. Sorry, current. I for current. Okay, so that's just a little hint that I wanted to give you about undoing those functions. And let's see here. So notice that the time scale that this thing decays at is equal to R times C. So that means that the larger resistance you have and the larger the capacitance you have, then the longer this decay takes to actually go down. Okay? So that's something that's important for us to notice, is that time constant is determined by which resistor you choose and which capacitor you choose. So one way to look at this is to say that the voltage is going to drop down to about 37% of its value. That's 1 over E. That number E is about 2.7. So if you take 1 over 2.7, you get about 0.37. So that's 37% of its original initial value after one of these taus, which is tau is this time scale set by R times C. And then after 2 of those taus, now you're down to 13%, and then so on and so on, right? So after one time constant, you're down basically about, 60% or so, right? So that's why that's kind of giving you, it's basically just a way to say, well, this is basically what the time scale is for the decay of voltage. Okay, so that's what the meaning is for when we're talking about the time scale. So, okay, so what if R was a mega ohm and C was 1 microfarad? What would be the time constant tau? Well, let's give that a try. So if R was equal to 1 mega ohm, which is 10 to the 6 ohms, and the capacitance was equal to 1 microfarad, so that's 1 times 10 to the minus 6, right, is farads, then you can see that tau is equal to R times C, which is 10 to the 6, times 10 to the minus 6, which is actually just 1, and the unit is going to be seconds. So again, not an obvious thing, but an ohm times a farad is just a second. Okay. So that would be a 1 second decay. That means that after 1 second here, you've gone down to about 37% of your original value. Okay, so for this RC circuit, if it originally had the voltage across the capacitor as 1 volt, what would be the voltage difference across the capacitor plates after 1 second? Well, we'd be down to 37%, so that means that we would be down to about 370 millivolts, or we would be at, so after 1 second, you could say that V is equal to V naught times e to the minus t over tau, but we already calculated tau, RC, as 1 second. And so if you then put in t is equal to 1 second, then you'd have V naught times e to the minus 1 over 1 second, right? So you'd basically say V naught times e to the minus 1, which is this 0.37 times V naught. And if V naught starts at 1 volt, then you'll have 0.37 volts, or if you want, 370 millivolts is another way of writing that. Okay, very good. So just wanted to mention that in a case that you're given a problem where it's asking for charging up the capacitor, you're going to see a very analogous type of situations. The current equation will be exactly the same, and the voltage across the capacitor, it's rather going to look like something like this, where the voltage is going to go up to some value like this, right? So this is going to be the voltage across the capacitor as a function of time, and the equation that you can use is going to be this one down here. Okay, so that'll be if you're asked about charging up a capacitor. So you might make yourself a little summary plot of plots for the current and voltage when you're charging up a capacitor and when you're discharging a capacitor. Okay, let's try a little challenge problem here. So here's the situation. We've got this this circuit. We've got a battery connected to a light bulb. There's a capacitor in here, but initially the switch is closed, and then we open it suddenly, and we want to know what happens to the brightness of the light bulb. Well, first, if it is closed, it looks to me like we're going to basically be ignoring this capacitor here. It doesn't really matter, because when the flow of current gets to here, it sees this capacitor, it's like, I'm not going to bother. I'm going to go through this open wire here. And so we'll have a current that's set by whatever this resistance is here. The moment that we open up the switch, though, what happens? Give you a moment to think about that. Please pause for a moment. See if you can think through what will happen in this situation when the switch opens. Well, when the switch opens here, maybe we can get a new piece of paper here. When the switch opens, here's my battery, here's my light bulb. I just draw light bulbs as a resistor. And then we've got this capacitor here. So what's going to happen in this situation is when this switch opens, as if this pathway is not even there. And now the current is going to go into charging up this capacitor. And so what's going to happen is that the voltage is going to slowly increase until it's charged up this capacitor. And the current is going to slowly decrease until the capacitor is fully charged. And so it's the current that ultimately makes the light bulb bright. And so what you'll actually see in this case is that the moment that you open that switch, that light bulb is going to get dimmer and dimmer and dimmer until finally it's not going to be on at all. So if you answered B, you are correct. The light bulb does get dimmer, and it just keeps on getting dimmer until it finally becomes basically off. Let's take a look at this might look like a really complicated problem, but I bet you can actually do it. So we've got some capacitors here, and they're initially charged up to 10 volts. Okay, so in other words, from this point right here to this point right here is 10 volts. And then the switch closes. At what time has the current in this 8 ohm resistor decayed to half of its value it had immediately after the switch closed? So you can think about this here and say, well, we're interested maybe in simplifying this circuit to something a little easier to handle, right? Let's try that. So let's think about this as like the 260 microfarad. We're going to basically just add them like 1 over, right? So we're going to do just like this, 1 over 60 plus 1 over 60. So that's 30 microfarads. So I'm going to already start to kind of rewrite this picture here as a 30 microfarad with a 20 microfarads as one side. Just maybe see if I can slide this over so you can see what I'm doing at the same time. Okay, so here's my 30 microfarads with the 20 microfarads. And we have a 30 with a 20 on the other side. So I'm going to do a 30 with a 20. So I guess that's 12, it looks like. So this side here is going to be 12 ohms with a 8 ohms. And then these guys are all connected together. Hopefully you have something like this, and then here's this little switch here, right? Well, now our work's a little bit easier because we know that capacitors that are in parallel with each other just add. So this is like a 50 microfarad capacitor. And then resistors that are in series just add. So this is like as if it was a 20 ohm resistor. So now we're reducing ourselves to a much simpler situation. It's just a circuit that has a resistor and a capacitor. So you like how we made it a little bit simpler now, right? Now the question is, we're initially V naught is 10 volts, and switch closes, and we want to know when the current in the 8 ohm resistor, which is the current in the whole thing, has decayed to half the value it had immediately after the switch closed. Okay, so now we have a problem, right? Let's look back at one of our formulas here. So one of our formulas said I is equal to I naught times e to the minus t over rc. That's what we need. I is equal to I naught times e to the minus t over rc. And if you remember, I could actually take the I over I naught over here, I over I naught, take the log of both sides, log of e to the minus t over rc, and I'll get minus t over rc is equal to I over I naught with a log. Now, maybe one of these tricks that maybe you don't know about, or it's been a while, is that if you flip these two here, you can actually turn this into a minus sign. So this can become a minus I naught over I is equal to minus t over rc. So in other words, the time that it takes is going to be rc times log of I naught, which is initial one, divided by I. So in other words, well, I guess the minus sign would have come out anyway if we did log of 1/2. So this is going to be log of, this is going to be twice as much as we then have you know, now. So I guess, I don't know, maybe however you want to look at it, I don't know what's the best for you, but if this starts off at, let's say, like 1 amp, and now this thing is at a half of an amp, then we'll do 1 divided by a half, and so we'll see RC times the log of 2. And then this R here is, of course, 20 ohms, and the capacitance here is 50 microfarads. So let's just plug all that stuff in together, and we'll say that we're going to have 20 multiplied by 50 micro, which is 10 to the minus 6, times the natural log, see how it says natural logarithm on there, of 2. So we get basically 6.9 times 10 to the minus 4 seconds is the amount of time that it takes. That's not really a lot of time, right? I mean, if you had 10 times 10 to the minus 4, that would be equal to 1 times 10 to the minus 3. That would be 1 millisecond, right? So it's even less than 1 millisecond is the amount of time that it takes for it to decay. Now it turns out that might seem like, wow, that's really fast. That's like faster than we'd ever be able to measure. Well, it turns out that idea is false. A millisecond and even microseconds is completely manageable for us to measure. And in fact, I have a friend who's working for one of these self-driving car companies, and I learned that they can actually, they're making more than 1 million computations per second of real-time data that's coming into your car through sensors such as LiDAR. So imagine 1 million times per second. A millionth of a second is a microsecond, right? And so if there's decisions that are happening on the microsecond time scale, then around a millisecond of measuring things is no problem at all. So that concludes our discussion about RC circuits, talking about capacitors, and then talking about the complex resistance. Next time we'll be taking a look at magnetism and the magnetic field. This will be chapter 24 is what we're focused on for next time. If you'd like to look ahead a little bit, one thing that you can take a look at besides this wonderful PHYS simulation here is you can also type in PHYS magnetism. In that case, you need Java, which is always one of those sort of pains. But if you just say allow it, maybe if you're using a Mac, you need to click like allow it, and you'll get something like this. And anyway, yeah, it's kind of old school. And you can see move this magnet around, and you can see the little compass moving around here. So we'll also take a look at that too. All right, have a good day, everybody. And I will, oh, you know what, actually I wanted to, sorry, one more thing. I wanted to also make a comment about one of the homework problems. So in the case for 23.81, I'll just write it here so it can be, and problem 23.81, there's like a battery. Let's see here, let me actually just get the, there's like a battery that's connected, there's a switch, and then there's a resistor, and then another resistor, like this. Okay, sorry, move to here. And I want to just help you to see something, is that the, if you think about like the voltage like across this guy here, you can, there's a supplemental video that's very helpful for figuring out what is that voltage across here, say compared with this point right here. And so that's kind of like a separate problem. If you work that and you say, okay, well, there's this much voltage here, it's 12 volts, it goes from here to here, right? And then you can actually calculate then what is the voltage drop across this guy here. And then there's a separate circuit here, which is a variable resistor and a capacitor that's shown here. Now this might just like at first sight look like, oh my gosh, it's so complicated. How do we ever solve something like this? Well, what you're looking for is you're trying to figure out the voltage across here compared with the voltage across here. And so they do that symbolically with, they said that there's a sensor across here. So the point is that this doesn't change, right? When you connect this, this switch here, this is going to be a steady current that flows through here, but it's not. It's going to be charging up over here. So in other words, you have, let's say, in terms of the amount of, if you have a constant current through here, that means that I times R is going to be the voltage drop across this guy right here, right? And you can figure out what that is, basically independent of this guy here, right? So you can say, yeah, does that make sense? So you can basically say, okay, I'm looking for when is the voltage drop, you know, so there's going to be some voltage drop here. I think it's going to be very close to the voltage drop of the 12-volt battery, but there will be something like, you know, so this is a constant voltage here, whereas across here, this one is rising, 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 and at some point in time, right, there's going to be some special time. Oops, there's going to be some special time where they cross. And that's what's really asking for. And the voltage drop across the capacitor is, of course, equals to this EMF of the battery times 1 minus e to the minus t over RC. So in other words, this is what you use for the charging up of a capacitor. And so you have to kind of rearrange things to figure out, well, which resistance is going to make it so that this thing actually crosses at this moment, and I think the moment, at least from my side, says something around, what is it, 15 seconds or 12 seconds? Yeah, so after a certain number of seconds that these things crosses is our special time. So I hope that helps. That's just one that occurred to me that maybe needs a little bit of explanation, but I think that a lot of them are quite straightforward and extensions of our practice. I invite you to post on the discussion forum your thoughts. Maybe there's some questions that need more clarification. Maybe there's some slides that need more clarifications. Please post your questions on the discussion board, and I'll try my best to monitor that and to post my responses there. Okay, thank you very much, everybody, for your attention. I'll look forward to. Well, I really look forward to seeing you all for real. We can also have some online meetings so we can brainstorm about that.